For decades, quantum computing has captivated the imagination of scientists and the public alike, often presented as a mystical leap in technological capability. Reports from institutions like IBM and Google suggest that these machines could one day solve problems currently intractable for even the most powerful supercomputers. But what exactly are these systems, and what are the true, grounded realities behind their almost mythical potential? This investigation seeks to demystify quantum computing, exploring both its profound promise and its formidable, often overlooked, limitations. At the core of all digital technology lies the classical bit, a fundamental unit of information existing in one of two states, 0 or 1. This binary system, as explained by pioneers like Claude Shannon, underpins every aspect of modern computing. Quantum computers, however, operate on fundamentally different principles. They utilize qubits, which, according to quantum mechanics, can represent not just a 0 or a 1, but astonishingly, both simultaneously. This departure from classical logic is where the extraordinary potential begins. The ability for a qubit to be both 0 and 1 at the same time is known as superposition, a core principle of quantum mechanics. As physicist Erwin Schrödinger famously illustrated with his thought experiment involving a cat in a box, a quantum system can exist in a combination of multiple states until it is observed. For a qubit, this means it doesn't have a definite value until measured. Researchers at institutions like Delft University of Technology have experimentally demonstrated this phenomenon, leveraging it as a building block for quantum computation. Even more perplexing than superposition is entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. When two qubits become entangled, their fates are intrinsically linked, regardless of the physical distance separating them. A measurement on one instantaneously influences the state of the other. Experiments conducted by Alan Aspect and others have repeatedly confirmed this bizarre correlation, solidifying entanglement as a real physical phenomenon. This profound connection allows quantum computers to perform operations across multiple qubits simultaneously, exponentially increasing processing power. So, how are superposition and entanglement harnessed for computation? Instead of processing bits sequentially, quantum computers can explore multiple possibilities simultaneously through superposition. Entanglement then allows these superposed states to interact in complex ways, generating patterns that would be impossible for classical machines. This parallel processing capability is the theoretical foundation of quantum speedup. As detailed in numerous academic papers, quantum algorithms, distinct from classical ones, are specifically designed to exploit these unique quantum phenomena to solve certain classes of problems far more efficiently. The conceptual journey of quantum computing began not in a hardware lab, but in theoretical physics. In the early 1980s, physicist Richard Feynman, observing the difficulty of simulating quantum systems with classical computers, proposed building machines that would obey quantum mechanical laws themselves. Paul Benioff later described a quantum mechanical model of a Turing machine, laying foundational theoretical groundwork. These early insights, further developed by scientists like David Deutsch, envisioned a new paradigm of computation, setting the stage for decades of research and development. One of the most widely discussed applications of quantum computers is their potential to break modern encryption. In 1994, mathematician Peter Shor published an algorithm demonstrating that a sufficiently powerful quantum computer could efficiently factor large numbers. This is critical because much of today's internet security, including RSA encryption, relies on the computational difficulty of factoring large prime numbers. While current quantum machines are far from executing Shor's algorithm on meaningful scales, the theoretical threat has spurred significant research into post-quantum cryptography by government agencies and private companies. The scope of quantum computing extends far beyond just breaking encryption. Researchers across various fields anticipate transformative applications. In materials science, quantum computers could simulate molecular interactions with unprecedented accuracy, leading to the discovery of novel materials with tailored properties for superconductors or high-efficiency batteries. Pharmaceutical companies envision accelerating drug discovery by modeling complex protein folding and chemical reactions, as detailed by studies from institutions like Merck and IBM. Financial institutions are exploring quantum algorithms for optimizing portfolios and detecting fraud, offering potential improvements over classical methods. Despite the theoretical promise, the practical reality of quantum computing remains in its infancy. Current quantum computers, like IBM's Q System 1 or Google's Sycamore processor, are experimental devices characterized by a relatively small number of qubits, typically in the tens or low hundreds, and significant error rates. As noted by experts from companies such as IonQ and D-Wave Systems, these machines are primarily tools for research and development, allowing scientists to test quantum algorithms and explore the behavior of quantum systems. They are not yet capable of tackling real-world problems beyond the reach of classical supercomputers. The primary adversary in the quest for stable quantum computers is decoherence. Qubits are exquisitely delicate, their quantum states, like superposition and entanglement, are easily disturbed by interactions with their environment. Even minute fluctuations in temperature, stray electromagnetic fields, or vibrations can cause a qubit to decohere, losing its quantum properties and collapsing into a classical state of 0 or 1. This rapid loss of coherence, often occurring within microseconds, severely limits the time available for computation and presents an immense engineering challenge, as documented by countless physics experiments. To combat decoherence and maintain reliable quantum operations, error correction is indispensable. However, quantum error correction is far more complex than its classical counterpart. You cannot simply copy a qubit state to create redundancy without disturbing it, due to the no-cloning theorem of quantum mechanics. Instead, researchers must entangle multiple physical qubits to encode the information of a single logical qubit. Estimates from sources like the Quantum Economic Development Consortium suggest that thousands of physical qubits might be required to form just one fault-tolerant logical qubit, demanding immense resources and intricate control systems. Building a stable quantum computer pushes the boundaries of engineering to extreme limits. Many leading qubit architectures, such as superconducting qubits used by IBM and Google, require operating temperatures colder than deep space, typically just a few millikelvin above absolute zero. This necessitates elaborate cryogenic cooling systems, often employing dilution refrigerators that consume significant energy and occupy large spaces. Furthermore, these systems must be shielded from all forms of environmental noise, requiring ultra-high vacuum environments and sophisticated electromagnetic isolation, as frequently highlighted by laboratory publications. Beyond simply cooling qubits, scaling up these systems presents monumental challenges. As the number of qubits increases, the complexity of controlling them grows exponentially. Each qubit often requires individual microwave pulses or laser beams to manipulate its state, leading to a wiring problem where millions of control lines would be needed for a large-scale quantum computer. Researchers at companies like Intel are exploring alternative architectures like silicon spin qubits, which might be more amenable to semiconductor manufacturing techniques, but the fundamental hurdles of interconnectivity and error rates remain substantial for all platforms. In 2019, Google announced it had achieved quantum supremacy with its Sycamore processor, claiming it performed a specific computational task in minutes that would take a classical supercomputer 10,000 years. This claim sparked considerable debate. IBM researchers, while acknowledging the achievement, argued that a classical supercomputer could complete the same task in days with optimized algorithms and sufficient memory, challenging the definition of supremacy. This disagreement highlights that quantum supremacy refers to a specific, engineered task, not a general-purpose computational advantage over classical machines for practical problems. It remains a proof-of-concept milestone. The current period of quantum computing development is often referred to as the noisy intermediate-scale quantum or NISQ era. This term, coined by physicist John Preskill, characterizes today's quantum devices as having tens to a few hundred qubits, but without the error correction necessary for truly fault-tolerant computation. These NISQ devices are valuable for exploring the boundaries of quantum physics and developing algorithms, but their inherent noise and limited qubit count mean they cannot yet reliably outperform classical computers for most practical applications. It is a vital research phase, but not yet the age of widespread quantum utility. Even if all engineering challenges were overcome, it is crucial to understand that quantum computers are not a universal panacea for all computational problems. As explained by quantum complexity theory, they excel at specific types of problems like factoring numbers or simulating quantum systems, where quantum phenomena provide an exponential speedup. For many other problems, however, classical computers remain equally or even more efficient. For instance, tasks like sending emails or browsing the web will not be performed faster by a quantum computer. It is a specialized tool, not a replacement for classical machines. The emergence of quantum technology also brings significant ethical and societal considerations. The potential to break current encryption raises urgent questions about data security and privacy for individuals, governments, and corporations. Beyond security, the development of powerful new computational tools could exacerbate existing inequalities, creating a digital divide between those who possess and control quantum capabilities and those who do not. Ethicists and policymakers, as documented in various governmental reports, are already grappling with these implications, aiming to ensure responsible development and governance of this transformative technology. The journey to building truly fault-tolerant, large-scale quantum computers is widely considered a marathon, not a sprint. Industry experts and national quantum initiatives consistently project that practical, error-corrected quantum machines are still many decades away. The path forward involves sustained international collaboration, massive investment in fundamental research, and breakthroughs in materials science, engineering, and quantum error correction. As articulated by numerous scientific consortia, incremental progress is the norm, with each step revealing new complexities and pushing the boundaries of what is currently technologically feasible. The story of quantum computing is, at its heart, a testament to human ingenuity and perseverance. Faced with fundamental physical limits, the fragility of quantum states, the demands of extreme environments, and the staggering complexity of control, scientists and engineers continue to innovate. This pursuit reflects a deeply ingrained human drive to understand the universe and to harness its laws for practical advancement. The challenges are profound, yet the commitment to exploring this new frontier of computation remains unwavering, pushing the very edge of what human technology can achieve. As we gaze into the future, quantum computing stands as one of the most exciting and challenging endeavors in modern science. It is a field that not only promises to revolutionize technology but also deepens our understanding of the universe itself, forcing us to confront the counterintuitive reality of quantum mechanics. Whether the grand visions of quantum supremacy will fully materialize in our lifetime, or whether fundamental physical limits will keep truly powerful quantum computers a distant dream, one thing is clear: the journey to unlock the full potential of quantum information is far from over, and its unfolding story will redefine the very limits of human technology.